In this video, we will study projectile motion. A projectile is an object that moves through the air after it has been launched, and we will assume that gravity is the only force affecting its motion. Let us begin by identifying the basic features and assumptions of projectile motion. Projectile motion is two-dimensional motion under the influence of gravity. Near Earth's surface, an object in free flight accelerates downward at approximately 9.8 meters per second squared. We normally choose the positive y direction to be upward. With that coordinate choice, the vertical acceleration is negative 9.8 meters per second squared. In the horizontal direction, we assume that the acceleration is zero. This means that the horizontal velocity remains constant. In the vertical direction, gravity continuously changes the vertical velocity. For the ideal projectile motion model, we neglect air resistance. This assumption allows us to treat the horizontal and vertical motions independently, even though they occur at the same time. When these two motions are combined, the object follows a parabolic path. The equations shown at the bottom summarize the accelerations. A sub y equals negative 9.8 meters per second squared and A sub x equals 0. These two facts are the foundation of the calculations that follow. Now let us examine the equations that describe the horizontal part of the motion. The equations at the top are the general constant acceleration kinematic equations written for the x direction. However, projectile motion is simpler in the horizontal direction because the acceleration is equals to 0 in horizontal direction. When the acceleration is 0 in the horizontal direction, the velocity in the horizontal direction do not change. If you look at the kinematic equation for the horizontal velocity, you can see if the acceleration is 0, then the final velocity and initial velocity is equals to each other. So we get the equation v sub x equals v sub 0 x, which is the initial velocity, and that is equals to a constant. That means throughout the flight, the horizontal velocity do not change. The horizontal position equation also becomes simpler. If you look at this equation, when the horizontal acceleration is 0, this term cancels out, leaving us with this part of the equation, which is x equals x sub 0 plus v sub 0 x times t. If we choose the launch point as x sub 0 equals 0, then the equation becomes x equals v sub 0 x times t. This tells us that the horizontal displacement is simply the constant horizontal velocity multiplied by the elapsed time. A useful idea to remember is that gravity does not reduce the horizontal velocity in this ideal model. Gravity acts vertically, not horizontally. The vertical motion is different because gravity produces a constant downward acceleration. The equations at the top are the general constant acceleration kinematic equations for the y direction. For projectile motion, The vertical acceleration a sub y is equals to negative g, which is approximately negative 9.8 meters per second square if we select upward as positive direction. Substituting negative g into the equations gives the projectile motion equations shown at the bottom. The vertical velocity v sub y is equals to v sub 0 y minus gt. The vertical position y is equals to y sub 0 plus v sub 0 y times t minus half gt square. We can also use the average velocity form y equals y sub 0 plus the quantity v sub 0 y plus v sub y divided by 2 times t. Another useful equation is v sub y squared equals v sub 0 y square minus 2g times y minus y sub 0. The best equation depends on which quantities are known and which quantity we need to find. For example, at maximum height, the vertical velocity is 0. That makes the equation involving v sub y squared specially convenient because time does not appear in it. Be careful with signs. If upward is positive, then upward displacement and upward velocity are positive, while the acceleration due to gravity is negative. We will now apply these ideas in an example. A place kicker launches a football with an initial speed of 22 meters per second at an angle of 40 degrees above the horizontal. We will ignore air resistance. The problem asks us three questions. First, what maximum height does the ball reach? Second, how long is the ball in the air from kickoff until landing? Third, what horizontal range does the ball travel? Before selecting equations, let us organize the physical situation. The ball begins at the launch point, rises while its vertical velocity decreases, reaches a maximum height where its vertical velocity is momentarily 0, and then falls back to the original vertical level that it was projected at. Meanwhile, its horizontal velocity remains constant. We will choose the launch point as x sub 0 equals 0 and y sub 0 equals 0. Because the ball lands at the same height from which it was kicked, its final vertical position is also y equals 0. The initial velocity is angled, so our first step must be to separate it into horizontal and vertical components. Let us calculate the two components of the initial velocity. The initial velocity vector has a magnitude of 22 meters per second and is directed 40 degrees above the positive x-axis. Because the angle is measured from the horizontal component is adjacent to the angle and the vertical component is opposite to the angle. Therefore, the initial horizontal velocity V sub 0x is equals to V sub 0 cosine theta. Substituting the values gives 22 meters per second times cosine 40 degrees, which is approximately equals to 17 meters per second. The initial vertical velocity is v sub 0 y equals v sub 0 sine theta. Substituting the values gives 22 meters per second times sine 40 degrees, which is approximately 14 meters per second. Both components are positive because the ball is launched to the right and upward. The horizontal component remains approximately 17 meters per second during the entire flight. The vertical component begins at approximately 14 meters per second, decreases because of gravity, becomes zero at the top, and then becomes negative while the ball is falling. These rounded components values will be used in the remaining calculations. We can now use the vertical component to determine the maximum height. For part A, we focus only on the vertical motion from the launch point to the highest point. Creating a table like this helps us to identify the known and unknown quantities. The vertical displacement y is unknown. The vertical acceleration is negative 9.8 meters per second squared. The vertical final velocity at the highest point of motion is equals to 0, and the vertical initial y velocity is 14 meters per second, and the time for the maximum height is also unknown. Once we identified the known and unknown values, the next step is to figure out the kinematic equation that is suitable for our problem. Now, if we look at these main kinematic equations, the first two involves time. In our data, we do not have time, so let's look at the third equation instead. So in this equation, we know the final y velocity, we know the initial y velocity, we know the acceleration in y direction, and we also know the initial y position, which is 0. So the only unknown thing in this equation is the final y position, and so that means we can use this third equation. So anytime you are trying to use a kinematic equation, you use this procedure. You look at the known values you have, and then you compare with these kinematic equations and pick the one that has least amount of unknown variables. So in this case, this third equation has the least amount of unknown variables, which is 1, right? So we don't know the final y position, but we know all the other things, so we can use that. So once we picked the correct equation, we rearrange it to find the final y position, and we substitute the values, and we find the maximum height is positive 10 meters. For part B, we have to find the time of flight. Time of flight means the time for the entire flight from the beginning to the end. So if we are talking about a projectile motion, it starts from here, goes to the end. So the time for this entire motion from here to here. All right. So in that case, the initial y position is, let's say, 0, then the final y position is also 0. And we can say the acceleration in y direction is negative 9.8 meters per second squared. And final y velocity, we don't know. Initial y velocity is 40 meters per second. And the time of flight is what we want to find. Now, next step is to pick the kinematic equation to solve the problem. So let's look at our equations. The first equation, we do not know the final y velocity, we do not know the time, so too many unknowns, so we can't use this one. And the third equation do not have time, so we can't use that. So let's look at the second equation here. We know the final y position, we know the initial y position, we know the initial y velocity, we know the acceleration, so the only unknown thing here is the time. So we pick this equation. All right, so y equals initial y velocity times t plus half times y acceleration times t square. And in this equation, we substitute the values. So we get 0 equals 14 meters per second times t plus half times negative 9.8 meters per second square times t square. Now, according to this equation, if t equals 0, this equation satisfies. So t equals 0 is one of the answers. But t equals 0 means the initial position. So this is not a answer that we want. It's not the time for the full flight. So we can further solve this equation, right? So we can divide both sides by the time. So one of these t's will cancels out with this square, and we get the version right here. And we can also multiply both sides by 2, so we get to this equation. And from here we can simplify and find t equals 2.9 seconds. So that is the time of flight. So now you notice we have two different times, t equals 0 and t equals 2.9 seconds, because if you look at this trajectory of this projectile motion, we have two places where you have y equals 0, and one place is at t equals 0 and the other place is at the t equals 2.9 seconds. So that's why we got two different values. But the correct answer here is 2.9 seconds. That is the time of flight. For part C, we need to find the range. The range is the horizontal displacement from the launch point to the landing point. In the horizontal direction, the acceleration is 0. So the horizontal position equation reduces to just the initial velocity in x direction times t, because this part is equals to 0. Now if we substitute the values, the initial velocity is 17 meters per second, and multiplied with the time of flight 2.9 seconds gives us the range 49 meters. Therefore, the football travels a horizontal range of about 49 meters. Let us summarize this example. The ball reaches a maximum height of approximately 10 meters, remains in the air for about 2.9 seconds, and travels approximately 49 meters horizontally. The main strategy was to separate the initial velocity into x and y components and then we used vertical motion to find the maximum height and time of flight, and then used the same flight time in the horizontal motion to find the range. The horizontal and vertical motions are analyzed separately, but they are connected by the common time variable.